All right, so we're going to talk a little bit more about the filtering concept that we've talked about in class. So, the idea here basically is I sort of formulated this in the context of a DC motor, right? If I applied a DC voltage to a DC motor, it would spin. But a more typical way to do that is to apply a voltage that looks like this guy right here. So it's a square wave, and the width of this pulse changes. Now, this is a square wave, so it's periodic, which means that it's represented by a Fourier series. And as that pulse width changes, the average value of the waveform changes. Now, because it's periodic, we know that it's a sum of sine waves, but the speed of the motor, if I run this correctly, is simply constant, or DC. And so somehow the motor is filtering out and not responding to all of those sine waves that must be present in that voltage. So we want to understand how that's happening. And that's our goal in trying to understand the filtering problem. Now, in general, we can think of phasor analysis. Phasor analysis is deeply related to Fourier transforms. The Fourier transform is the general approach for analyzing any kind of a system, whereas phasors really apply specifically to the circuit problem. All right, so let's look at the circuit problem a little bit. This will help us to think a little bit about how we approach this. If I have a general input here, the voltage on a capacitor is Cn cosine n omega naught t plus theta n like this. I know that the current in the capacitor is IC of t equals C dVc dt. And I can basically take the derivative of that voltage to figure out what the current's going to be. That tells us that IC of t, Vc of t, those are things that exist in the time domain. That means in the real world. In other words, we have a voltage that's pulsating up and down as time advances. All right, but we often analyze that in the phasor domain. And the phasor domain analysis essentially comes from the fact that I can represent this guy as the real part of Cn e to the j theta n e to the j n omega naught t, where we typically call this Cn e to the j theta n our phasor, okay? And often times you guys write that as Cn with an angle theta n, okay? Now, what we do when we analyze this in the time domain is we basically end up saying that, well, we'll do analysis with the phasor and say we have Cn e to the j theta n. Let me be careful, right? I have C times the derivative of Cn e to the j theta n e to the j n omega naught t, like that. So what that tells me is I end up with j omega naught n times C times Cn e to the j theta n e to the j n omega naught t. Now, what we do is we say, okay, well, in steady state, we know that if I have a sine wave in, I'm going to get a sine wave out. So essentially the current is going to also be the real part of this result. And so we get kind of an interesting result that we end up utilizing. So in phasor analysis, what you end up saying from this, right, is I end up referring to j n omega naught c as essentially it's 1 over the impedance, okay? And what we end up saying is that the phasor for the current is 1 over the impedance times the phasor for the voltage, V sub c. And that phasor for the voltage is given by that guy, okay? Now you've been doing that all along, and it basically comes out from this analysis. And the impedance got sort of derived by taking that derivative. Now, phasor analysis is deeply related to the Fourier transform, okay? And we've talked about this sort of a number of times in the past, but what I'll do is I'll look at this guy right here and I'll say, all right, well, let's express the Fourier transform of V sub c of t. So V sub c of t is what we have in the real world, in the time domain, okay? And that's a function of time, okay? But V sub c of omega is in the frequency domain, or It's a function of frequency. So to perform our analysis, what we do is v sub c of t is what happens in the real world, but we transform over into this other domain where analysis becomes a lot easier. We just represent this waveform that's changing as a function of time by basically just two numbers, an angle and a magnitude. And to do that, right, we can use this expression here, real part of that expression, to represent this cosine that exists in time. And then we can also use Euler's identity to represent this guy. Now, by using Euler's identity, it's easy to show that alpha n is going to be Cn over 2 with an angle of theta n, and alpha n minus 1, or sorry, alpha minus n is Cn over 2, and it has the opposite angle, okay? And the way we said we do this is we say, well, at the frequency n omega naught, I say this guy has a magnitude alpha n, which is Cn over 2, and an alpha minus n magnitude, which is the same, at negative n omega naught, and a negative theta n here at negative n omega naught, and at n omega naught, an angle theta n, okay? All right, so how do we approach this guy? So essentially we say, okay, this is what that Fourier transform looks like. One of the critical things we realize here is if I look at the Fourier transform is a function of frequency. So if I evaluate it at n omega naught, I see that it's equal to Cn over 2 with an angle of theta n. And boy, that's a lot like the phasor, right? In fact, it looks like the phasor is essentially 2 times Cn over 2 times the angle there. So in other words, I could think of it as 2 times the value of the Fourier transform at that particular frequency. So notice what I'm doing. The Fourier transform is a function of frequency. I am evaluating it specifically at omega equal to n omega naught. I'm evaluating it at a particular number. Now, I say all of this to suggest something that I think you guys already know, which is if I essentially, right, well, I'm going to use it for something that you guys already know, but essentially the really key result from this is phasor analysis and Fourier transform are really closely related to each other. So if I have a expression in time that looks like what I just circled there, that expression in time has a phasor, which you guys have talked about plenty of times before, which is given by a magnitude and an angle. That phasor is equal to 2 times the value of the Fourier transform at that particular frequency. And so for this particular reason, the analysis using the Fourier transform is often called frequency domain analysis, and it's a more general form of phasor analysis, but they're very closely related to each other. All right. Now this is all important because, you know, if I have a circuit, things are relatively straightforward for analysis purposes when I deal with sine waves. When I have an electromechanical system or something like that, it becomes a little bit more complicated. So looking at this circuit, we already said this before, I sub c of t equals c dvc dt. And I've been given this v sub c right here. All right. And yeah, as we said, we can represent this guy as the real part of the phasor Cn angle theta n times e to the j n omega naught t, like so. Okay. Plug that in here. And what if we, you know, just remember that we need to take the real part when we're all done, what that tells us is we get an IC of t that becomes c times j omega naught n times Cn angle theta n times e to the j n omega naught t. In other words, every time we plug in an e to the j n omega naught t into a derivative expression, a j n omega naught appears here at the front. Okay. Now, because of the fact that I sub c of t is also going to have an e to the j n omega naught in it, what we end up always saying is that the phasor for that current, okay, is equal to, in this case, J n omega naught times C times the phasor for that voltage. And I can relate the phasors of the voltages, which means that I can effectively relate not just their phasors, but also their Fourier transforms, like that, okay? So that kind of gives us an important result, right? So what it says is, I can take an expression, if I'm taking the derivative of a time domain expression, I can move that into the frequency domain, replace V of t with V of omega, and replace the derivative, right? So if I have d by dt of V of t, okay, I can replace the V of t with V of omega, and I can replace the d by dt with a j omega. So if I take the kth derivative, I replace that with the j omega to the kth power. All right. This here is the Fourier transform of the derivative. All right. In this case, the one I show on the left is the Fourier transform of the kth derivative. This guy is the Fourier transform of the first derivative. Now I can use that in a lot of general cases. So let's say I had something like this. All right. So I'm given an input, this guy. So that input is V sub s of t in this case. Okay. So what I can do is I can replace V of t with, so I'll replace V of t with the Fourier transform of it. And I'll replace Vs of t with its Fourier transform. And then I replace all the derivatives using the rule that I just showed here, okay? So let's go through that. Over on this side, the right side of the equation, Vs of t becomes Vs of omega, okay? That's pretty straightforward. Now, over here, this is a little bit more complicated. So I have the A naught V of t. So V of t gets replaced with V of omega, and I simply write the A naught. Now, here I come to the first derivative term. So I write V of omega. I replace the d by dt with j omega and multiply that by A1. And then I can keep going. All right, so I'll take this k minus 1 derivative term. I replace the V of t with the V of omega, and I replace the kth derivative here with, or the k minus 1th derivative, with j omega to the k minus 1 power, and multiply that by this coefficient ak minus 1. And then when it comes to the highest derivative, highest order derivative, I would replace the derivative with j omega to the kth power and replace V of t with V of omega. Now, if I look, every term here on the left side has a V of omega. So I can write this guy as, I can factor out the V of omega. All right, and then I have here j omega to the kth power plus a k minus 1 times j omega to the k minus 1th power. And then that extends to a1 times j omega plus a0, and that's all equal to Vs of omega. Now, the way that I express this is I usually rewrite it like this. V of omega, the Fourier transform of the output of the system, is Vs of omega, the Fourier transform of the input, over j omega to the kth power. So basically everything in the square brackets there. Now, this result is essentially the same thing you get when you use impedance analysis. All right, impedance analysis basically exploits this result without you guys having ever really fully talked about that in 2112. This is the more general form of that result. And what I do is I call this expression here basically 1 over all of that. I call that guy h of omega, the transfer function. So the transfer function is a Fourier transform. And I'm saying the Fourier transform of the output is equal to the transfer function times the Fourier transform of the input. Okay? So when I have a circuit, what that sort of says is something that you wouldn't normally do, but I could take the differential equation and I could I could use everything we just did to transform the differential equation into the frequency domain. All right, so what's important about that, so in this case we say is, well, if I got the differential equation and I do KVL to get that, you should be able to do that. I would have Vn of t is equal to RC dV out by dt plus V out, right? What you do is you say, okay, I can replace the Vn of t and the V out of t with their Fourier transform. So Vn of omega is equal to RC times J omega replaces the d by dt. V out of omega replaces the V out of t, and V out of omega replaces the V out of t. So I can rearrange this and get that V out of omega is equal to Vn of omega over J omega RC plus 1. And I have that my transfer function, h of omega, is 1 over J omega RC plus 1. Okay, so we'll write this, guys, h of omega times Vn of omega. Now that's the same result you would get from impedance analysis, right? What's nice about this is what it's saying is h of omega is a function of omega. And that allows me to say, well, what if I have sine waves at different frequencies? What's the response of the system if I change the frequency of that input? So you're used to solving problems in circuits where you're given a particular frequency. You're told that your input is at 1 kilohertz or 2 kilohertz or whatever. But it's sometimes useful to keep it as a function of frequency so we can do some design, right? Which is much more useful to us in general. Now, if I get this particular result, once I have this, what it says is, if I have a sine wave at a particular frequency, I plug in that value of omega and I solve for the Fourier transform at that frequency. And then I can inverse transform that, which is basically just to go from a phasor to the time domain. All right. So sometimes, you know, when I'm in the frequency domain, I'll basically, instead of saying I have Vn of t and V out of t, I will express these guys using their Fourier transforms, right? Which is just like using phasors. The only thing is different, right, is we say if I have a phasor, the phasor is 2 times the phasor at n omega naught is equal to the Fourier transform, Fourier transform at that frequency, okay? All right, so I'm gonna use this, basically I have 4 steps here. So what I do is I determine the Fourier transform of the input. That's basically figuring out the phasor. Then I determine the transfer function using this approach that we've talked about here. Then I basically multiply h of omega, the transfer function, by the Fourier transform of the input to get the Fourier transform of the output. And then I go and I perform the inverse transform, remembering to multiply by 2. Okay, there's 2 reasons for multiplying by 2. One is the fact that the Fourier transform assumes complex exponentials where the amplitude is always half of what it is for the true cosine wave. Okay, so we kind of derived that before. Just remember that you're gonna have to bring that factor of 2 in there, right? The reason I think about that is because when you're using the Fourier transform, half of the energy is the positive frequency, half of the energy is at the negative frequency, okay? So multiplying by 2 allows me to just say, well, I'll do the analysis at one of the frequencies. And that way I have half the analysis to do. I just multiply the result by 2. All right, so let's use those steps. So let's say I've got this circuit that has sort of a more complicated input, like what I have right here. So this is a Fourier series with a fundamental frequency of 60 hertz. It does not, as we have in this table here, it does not have a second harmonic at 120 hertz, but it does have a 180 hertz, so a third harmonic, and it does have a DC term, okay? Now you should be able to figure out how to get the Fourier transform that I showed right here. I've talked about that before, so I'm not going to talk about it more in this video. There's other videos that talk about that. Now, what I want to do, that's step 1, right? So now I've got the Fourier transform of that input. Now what I want to do is I want to go through and I want to figure out the transfer function, okay? So to get the transfer function, I say, okay, well, if I had for the circuit the differential equation, V in of t equals RC dV out by dt plus V out, I can use the approach we just described to figure out the transfer function. Now you might be saying, well, I could just use impedance analysis, and you can, right? If I have a circuit. But what if I have a system like that DC motor I showed at the beginning, where I have a mechanical component and an electrical component? What do I do then? Well, in that case, I'm stuck with looking at looking at differential equations. Okay, so and you'll need that in the project. So to do this, to figure out the transfer function, we've done this a couple of times already. I replace the V in of t with V in of omega. On this side, I replace all the V out of t's with V out of omega. And I replace the derivative with the j omega. So this guy becomes j omega RC, this would be a big C, plus 1 times V out of omega. And you can just distribute this to see where that comes from. So that tells us my h of omega is 1 over j omega RC plus 1, right? And so I have that V out of omega equals h of omega times V in of omega. So what I need to do is to figure out the value of V out of omega at each of the frequencies that we looked at over here. So at DC, 60 hertz, and 180 hertz. All right, so let's start that process. All right, so at the first frequency, at omega equal to 0, what we saw was that V in at 0 was equal to 5. All right, V in at 0 was equal to 5. So I want to figure out that V out of 0 is h of 0 times V in of 0. Now, what we typically do here is to look at the transfer function as a function of frequency. So in this particular case, and all throughout this problem, all right, I am assuming that the RC value, and I'll write it over here. This is not true in general, but I just chose components RC so that they were 1 over 2 pi 60. So somehow an R and a C were chosen to match that value. Now, when I'm designing, I often do that. I often say, well, I want RC to be a particular number, and I go to the drawer to find components that actually match that value. All right, we'll see some examples of that. All right, so what I typically do, so h of omega here, okay, is 1 over j omega RC plus 1. And given the values that I've given you, that's 1 over j omega over 2 pi 60 plus 1, okay, like that. So what that is, that's a complex function of frequency, right? Meaning it has a magnitude, right, and an angle, like that. So what that means is I have to plot the magnitude versus frequency, which is what I've got here, and the angle versus frequency. And I've got some code to do that. So in this case, what I did was I generated an omega vector, which goes from 0 to 2000 in steps of 1. And then I evaluated h at those frequencies. Now notice I have 1 dot divide. And the reason I have dot divide is I want to take 1 over each element in the omega vector here, okay? All right, so 1 over each element, and I guess what is ultimately the denominator vector. All right, so if you look at the graph that I've got here, here's the code to actually do it, right? So I'm plotting the magnitude in the top graph and the angle in the bottom graph, okay? And what I can do is I can look at this graph to say, well, what is the value of the transfer function at those particular frequencies? So when I'm looking at DC in this case, all right, so DC is omega equal to 0. So my x-axis value is 0. It says that my magnitude h of 0 is equal to apparently 1, okay? It's equal to 1. And the angle of h of 0 is equal to 0 degrees. So if I have V out of 0 equal to h of 0 times V in of 0, V in of 0, if we go back a couple of slides, is 5. H of 0 is 1. Maybe I'll write them in order. H of 0 is 1. V in of 0 is 5. So V out of 0 is 5. And when I inverse transform that, at DC, I get that V out of T is equal to 5 volts. Okay. All right, very simple. Input equals output in that particular case. Now we use this graph a lot. All right, now let's use it specifically. So at the next frequency is specifically omega equal to 2 pi 60. Okay, 2 pi 60. So if I go back over here to look at the Fourier transform of the input, I see that the Fourier transform of the input had a magnitude of 2 at that frequency and an angle of 60 degrees. Okay, so at that frequency, all right, so V in of 2 pi 60, the Fourier transform there has a magnitude of 2 and an angle of 60 degrees. So it's sinusoidal, okay? So what am I going to do here, right? Well, I know that V out of 2 pi 60 is equal to H of 2 pi 60 times V in at 2 pi 60, okay? And this is going to be some complex result that represents a sine wave, right? It's a Fourier transform of some sine wave. So again, I'll do the same thing. So I basically plotted this transfer function versus frequency. And I went to omega equal to 2 pi 60, which is approximately 377 radians per second. All right. I went there. And so what I see is at omega equal to 377, which is approximately 2 pi 60, I see that the magnitude of h of 2 pi 60, the magnitude there, according to this top graph, is 0.7071. And the angle at that frequency is equal to apparently negative 45 degrees. Okay, so that tells me that V out of 2 pi, V out at 2 pi 60, the Fourier transform at that frequency is 0.7071 e to the negative j 45 degrees times the Fourier transform of the input at that frequency. All right, so and at that frequency in particular, being 2 pi 60. All right, we had that written out here a couple of slides back. It was 2 angle 60. So let's write it 0.7071 angle negative 45 degrees times 2 angle 60 degrees. And so my result becomes simply 2 times 0.7071 with an angle of 15 degrees. Okay, so because the phasor is 2 times the Fourier transform, that means that V out of t at that point is going to be 2 times 0.7071 times cosine 2 pi 60t plus 15 degrees. Okay. All right. So what this tells me is that the output got a little bit smaller, right? The output is basically about 70% of what it would have been at DC, which is an interesting fact, right? So let's kind of keep going with this, right? So we have one more frequency to look at. So this case is omega equal to 2 pi 180 radians per second, okay? And V in at 2 pi 180, if I look at that, if I go back a couple of slides, that was equal to a magnitude of 3 with an angle of -90. Okay, magnitude of 3 with an angle of -90. 3 angle -90. Okay, and I know that V out of 2 pi 180, so the Fourier transform at 2 pi 180 is equal to H at 2 pi 180 times the in at 2 pi 180, or H at 2 pi 180 times 3 angle -90 degrees. Okay, so we got to figure out what is the magnitude and the angle of H at that frequency, 2 pi 180. So again, I make another plot, right? In this case, omega equal to 2 pi 180 is approximately equal to 1131 radians per second. So what this tells me is that the magnitude's gotten even smaller at that point. The magnitude at H of 2 pi 180 is equal to, apparently, 0.3162, and the angle at that frequency is apparently, from the bottom graph, -71.57 degrees. Okay, so in that particular case, what this is telling me is V out, the Fourier transform at that frequency, 2 pi 180, is equal to the transfer function at that frequency times the Fourier transform of the input at that frequency. All right, so that means I have 0.3162 with an angle of -71.57 degrees times, if you look back a couple of slides, it's 3 angle -90 degrees. So that tells me I have 3 times 0.3162 with an angle of -90 minus 71.57 becomes -161.57 degrees, like that. Or that my output in the real world, V out of t, notice my time domain stuff I usually write with lowercase v's, and I write my frequency domain with uppercase v's. That's pretty standard. That's going to be 2 times the Fourier transform magnitude at that frequency times cosine 2 pi 180t minus 161.57 degrees. Okay? Important thing to note is that at this frequency and at the other frequency I looked at, it appears that my output is actually smaller than my input, right? So in fact, it looks like my output is going to be 31% of the size of my input at 2 pi 180. And at 2 pi 60, my output's going to be about 70% of my input. All right, that's a really important result, and we use that result a lot. All right, so what it says is my output is going to be 5 plus 2 times 0.7071 cosine 2 pi 60t plus 15 degrees plus 2 times 3 times 0.3162, I guess what we had. Yeah, 0.3162 times cosine 2 pi 180 t minus 161.57 degrees. All right, if you compare that to our original input, that was 5 plus 2 times 2 cosine 2 pi 60t plus 60 degrees plus 2 times 3 cosine 2 pi 180 t minus 90 degrees. Okay, so the important thing is it looks like if you compare like to like, if you compare the 60 hertz term to the 60 hertz term, the output term is smaller, right, by about 70%. And at the case of 180 hertz, you see the output is smaller by about 31%. So that's kind of an important result. And I can kind of see it clearly here when I look at the transfer function as a function of frequency. I can see that as the frequency goes, the frequencies of my inputs go higher and higher, the magnitude of the output's getting smaller and smaller, and the phase shift looks like it's tending towards negative 90 degrees. Now, this graph is really useful, but the problem I can run into is what happens when I have an input like this. So I have one input at 60 hertz, and I have another one at 2 million radians per second. Now, that's actually pretty common to have waveforms like that. And we see that a lot of times when we look at, let's say, a solar converter, when we're trying to interface a solar panel to the grid, or when we're trying to drive a motor. We see this type of thing all the time. Now here, I did this for the same circuit. H of omega is 1 over j omega over 2 pi 60 plus 1. Here's what happens when I plot that. You can see it starts at 1 and then it gets really small and just stays small, okay? And then here, I see that the angle just tends towards negative 90. Now the problem is this guy is not actually 0. And I can say it's approximately 0, but it's not actually 0. It's really hard to even look at that graph. And what we do as engineers is we don't like to look at that graph. If what I do is instead of plotting omega on what I call a linear scale like this, what I often do is I look at the log base 10 of omega. If you take the log, what that does is it expands the frequency domain out a little bit. And I end up getting this. So notice here, what I have on the left side, this is a linear scale. And what I have here is a log 10 scale. All right, the log 10 scale looks pretty different. But if you see what I'm looking at here, I have even spacing between the different marks on the screen. In this case, I'm doing basically the same range, pretty close to 0, 10 to the minus 2 radians per second, up to 10 to the 6 radians per second. All right, so a pretty similar range. But if you notice, what I'm looking at here is a much cleaner graph. I can really see a lot better on the logarithmic scale than I do on the linear scale. It's showing the exact same thing. All right, but it's doing so using a logarithmic scale rather than a linear scale. Now, instead of plotting the magnitude, the thing that's really weird about this is I plotted the log of the magnitude. That helps as well to deal with the fact that this guy is getting so tiny as frequency gets bigger. So I plotted the log of the magnitude, and for what reasons that are somewhat historic, we multiply that by 20. All right, so let's see where we would use this. All right, we'll use this with a simple example at DC. Now, to figure out how I did that, in MATLAB, what I do is I'm going to generate my omega vector using what I call the log space command. And you can type help log space to figure out how that works. But basically, this command here is saying, give me 10,000 points, so starting at 10 to the minus 2, that's what the minus 2 means, and going to 10 to the 6th. That's what the 6 means. And put 10,000 points between them. And then evaluate H at those frequencies. So I reevaluated H. And again, remember the dot divide, because the denominator here, I want to get 1 over the value of the denominator at each frequency. Now to plot that, what I did was I used the semi-log command. Semi-log means I want to make a graph where one axis is logarithmic. So in this case, log x means make semi-log x means make the x-axis logarithmic, but make the y-axis linear. And what I did was I simply plotted 20 times the log of the magnitude. And for the angle, what I did was I said, okay, give me semi-log x means I want to plot just the logarithm of the x coordinate. And then I'm just going to plot the angle as the y coordinate. right? That's how I generate the graph like I have shown here on the left. Now, how would I use this? All right, so let's say I'm looking at DC. So I know that I know that V out of 0 equals H of 0 times V in of 0. All right, and I know that V in of 0 equals 5. So how do I use this graph here to figure out what H of 0 is? Now, problem I have on the logarithmic scale, I can never actually show 0. All right, but that's kind of okay because I know what's happening. As I get to smaller and smaller and smaller frequencies, this guy just approaches 0. All right, same with this here. Right, so the angle is very clearly 0. We already even know that that's the exact answer. But let's look at how we use the magnitude here. All right, so what this says is that 20 log 10 of the magnitude of H of 0 is equal to 0. Okay, that's what this says. So to figure out the actual magnitude, I got to divide both sides by 20. I get the log 10 of the magnitude is equal to 0. And then I raise both sides to the power of 10. So I go 10 to that and 10 to the 0. So that gives me, so 10 to the log of something gives me the argument. And I get that's equal to 10 to the 0 or 1. So I get what I already knew, right? Which is that 1 is my value of H of 0 times 5. So V out of 0 is equal to 5. Now, moving forward, we'll look at how we use that at other frequencies, but it's pretty straightforward. All right, it's not particularly hard to do. And we'll stop there.